Hey guys, we'll make a little video on quantum. So here we go. If I was doing this in class, I'd start off by talking about a guy by the name of Max Planck, and Max was a physicist and did a lot of work in this area as far as quantum mechanics goes. The thing about him is he came up with a bunch of different relationships, and the big one here is this right here. It's called Planck's hypothesis. It's the relationship between the energy of a photon of light and that light's frequency. So the thing about light is that it's a particle as well as a wave, and it's one of those strange things. It's hard to understand, but it can display properties of both at almost the same time, right? So it can act as a wave, that's why it has an actual frequency, but then it also can be thought of as a little packet of something, a packet of energy. So anyway, he came up with this. Here's the equation. This is the photon energy. This is the frequency of that photon of light, even though it's a photon. So it's one discrete particle of stuff, but at the same time it has a frequency because it also is a wave. Okay. And then this is H is called Planck's constant, 663 E negative 34, and that's a thing. All right. Okay, so if we keep talking about this, we're going to combine a few equations here. And we're just going to fiddle with this a minute. So this equation is something that you probably should have seen. That's the velocity of a wave. And since light is a wave, then it has a velocity. And of course, we know the velocity of light. We call that c. That is the velocity of light, right? And so since we're talking about light, the velocity of light is called c. So then we're going to replace v with c. So there you go. Okay. Now, what we're going to do next is bring that new equation we had back in. That sucker right there. Okay. Now you see that they both have f. So what I'm going to do is I can solve this equation for f. So f is equal to c over lambda, right? And I can stick that in here. Okay. And I get this new equation. E equals h c over lambda, which is just another way of writing this thing. So these two equations are a thing. Now that the trash truck is gone. Anyway, as I was saying, these are a thing. Now, this sucker really, I don't write it in, I leave that out, so it actually looks something like this. And so you get hc over lambda. Now the deal here is h times c, those are both constants. H is Planck's constant, c is the speed of light, which is a constant, right? And so when you multiply those two together, you get this equation. That equation is really handy. It can be used in a lot of different ways. The only caveat here is that this lambda, right, has to be in nanometers. It's got to be in nanometers in order for this to work, right? So energy is usually measured in something called electron volts, which is just another unit of energy, right? Electron volts. Electron volts is very similar to joules. In fact, you actually use joules in order to get there, but it's just another unit for energy. So one of the ways we can calculate certain things is using these equations. One of the neat things about this is we can figure certain things out, like how hot is the sun. You can't get close to the sun because it's so hot, right? And if you try to get any type of measuring device near the sun, it'll melt, right? Long before you actually get there. So one of the things that we do is that we can use this to try to figure out how hot parts of the sun are. So we know that the wavelength of light given off by the sun is a certain wavelength, right? So let's say it's 550 nanometers, right? So what would the energy of a photon of light from the sun be? You can use this. Well, 40 over 550 is around 2.25 electron volts, 2.25, and we can use this. All right, so speaking of the sun, the sun is something we actually call a black body. These are objects that actually absorb wavelengths of light, and so the sun's odd because it also, of course, gives off a lot of wavelengths, but it's something that's going to absorb a lot of wavelengths too. But in this section here, we were talking about how do we know how hot the sun is because you can't get close to it. So what we do is we actually analyze the wavelengths of light that it gives off. And a dude who figured some stuff out, his name was Wien, and figured out that there's a relationship between how hot something is and the wavelengths that it gives off. And this is very handy because we can use this to figure out what are the temperatures of things, right? And then you guys probably know this, but I'll just say it. As the temperature goes up for something, the color changes, right? So if you look at the wavelengths of light that our sun gives off, the average is about 550 or so. So our star is kind of in the middle here. It's sort of a yellow star. Red would be on the low end, and blue to white would be on the high end. And so our star is a yellow star because it gives off this average wavelength. Okay, so with all that being said, there's an equation that you need. My board's set up here. I need to pause this. So the equation looks like this. I'm talking about this guy Wien. He figured this out, right? The equation is lambda times T. Lambda is the wavelength. T is the temperature. It's in Kelvin. And it's equal to this constant. So this constant is Kelvin meters because this is a wavelength and this is a temperature, right? And so what we can do here is we can fiddle around with this, and say, all right, well, like before we said that our star has a wavelength about 550 nanometers, right? And so if I solve for T, right? So I can do this, 2.9 e negative 3 divided by wavelength, which is 550 nanometers, right? So I got to change that because this is in Kelvin meters, so 2.9 e negative 3 over 550 e negative 9. So I have to convert that. But anyway, you end up with around 5200 Kelvin, which is pretty hot, So this equation is really handy as far as this relationship between the wavelength and the temperature of things. Okay, so back to light and how it's weird. Light is a wave as well as a particle. It shows both of these characteristics. We just need to talk about where light comes from. We're going to use the hydrogen atom, mostly because hydrogen is very simple. It's easy to deal with. We know a lot about it. I'm hoping that you looked at all the notes. So you looked at all the different theories of, how the atom looks, how is it constructed, from Dalton to Thomson to Rutherford, finally to Niels Bohr. So we know that there's this center part, which is called the nucleus, and then you have this area on the outside where you have all these electrons flying around, and we know that they're hard to spot. You really can't. And we talk about these little areas as if you can only figure out the probability that that an electron will be at a certain spot in a certain time, right? But this is how we like to think, about how things work. A lot of people call it the planetary model, right? So you have the sun in the middle and all the planets going around. And this is how I kind of think about atoms, right? So the nucleus is in the center, and then you have electrons that are in certain areas, right? Now, if they're closer to, then they don't have quite as much energy. This is called, so this very first little level here is called the ground state. And as they can go up, right? So, where does light come from? Electrons can get bombarded by energy, and when they get excited, and they can get excited, and they jump, and they make these jumps, and they can go from 1 to 2, or 1 to 3, or 1 to 4, things like this, right? And so they get excited, and they jump. When they jump to a different level, depending on how much energy that they get, where are they getting this from? They're probably getting hit by other photons of light that are very energetic. And if it's energetic enough, that amount of energy can actually get them to jump to different places, right? Now, they don't stay there for very long, and then what happens is they then fall back to where they were. So if it jumps from first to second, and then they're going to fall back down. When they make that jump back down, or they fall back down, they're going to let off a certain amount of energy, and that is a photon of light. So if we have one electron that's on this first energy level here, it makes the jump up to maybe the second. When it falls back down, it will let off a little photon. And that photon has a certain amount of energy. And that is light. The wavelength of that photon will tell you, essentially, how much energy it has, what its color is. And so when people ask, why is the sky blue? It's because our atmosphere is made of, it has certain gases. And those photons are going to give off a certain wavelength. And it just happens to be kind of in the bluish area. The bluish, most of the gas that we live in is nitrogen with a little bit of oxygen, carbon dioxide, and so you get certain photons with certain wavelengths, and they give off certain colors, and it just happens to be blue, and that's why the sky is blue. So anyway, electrons can get excited; they jump up. All right. So for hydrogen, the ground state, the energy of an electron in the ground state is negative 13.6 for this particular atom. Okay, so that's the ground state. So this first level here is, what color? 13.6. Negative 13.6. It's kind of small. I'll zoom in. So it's negative 13.6. This is the relationship here. So if you want to know for the second E2, that'd be negative 13.6 divided by 2 squared, okay, which is going to be negative 3.4. So for E2, the second, right, negative 3.4. For the energy level of the third, negative 13.6 divided by 3 squared is 6. Okay, which you end up with negative 1.5. 1.5. So this is the thing. Now the question is, why do all these numbers have little negative signs? This is one of those things that's kind of hard to teach. What we're doing, if you have an electron in this ground state, that's like being in a hole. The electron is sitting in a hole, and it's like you. Let's say that you get stuck in this very deep hole. And I do this in class. I use a big trash can, so it looks kind of silly, but I have to pause.